Thanks, Tor, for organizing the session together with Nico, and thanks for inviting me, and thanks for coming back from lunch. So my talk is not up here. Oh, yes, it is. It is about establishing causal relationships in neuroimaging, pitfalls and promises. And so it's pretty clear that neuroscientists have become increasingly interested in trying to use neuroimaging data to make sort of causal inferences, as causal statements about brain function. And so often, is there an echo? No, it's just here. Okay. Often the methods that are used for modeling these associations among variables are then used to make causal inferences with these associations sort of equated with causation. However, one of the problems with the field is that there's rarely, if ever, a statement of what notion of causation, if any, sort of underpins such claims. And this is sort of problematic both for basic neurosciences and clinical practice. And so the idea is that, making causal relationships in the brain is some sort of holy grail of sort of trying to understand how the brain works. And what I'm going to try to argue is that we haven't really even defined what it is that we're looking for, and I think that's a sort of a huge shortcoming. And so to sort of illustrate, let's look at where causation is often talked about, and that's in effective connectivity. And so effective connectivity is defined as the directed influence of one brain region on the physiological activity recorded in other brain regions. And so here, the claims to make statements about sort of causal effects among tasks and regions. And you can see that this is true by looking at the names of some of these methods that are used to assess effective connectivity. We have Granger causality, dynamic causal modeling. And so the goal of these methods it becomes quite clear from the name itself. And so let's just sort of look at the state of the field with regards to causation and things like that. Let's take a look at Granger causality and dynamic causal modeling, because what I want to argue is that sometimes the type of causation that they're sort of showing or may not align necessarily, if they're at all defined, with what we might want. So let's start with Granger causality. And so this was originally developed in econometrics or in economics literature, but has then since been applied to effective connectivity. And here, the definition of causality, which they call Granger causality or G-cause, is that a variable z is said to G-cause another, or Granger cause, another variable y, if the past of z contains information that helps predict the future of y of and beyond the information already in the past of y itself. So that's the definition that's usually given. So it's something about like saying, well, the past of activation in this brain region, if it's predictive of the current value in this brain region, well, then there's a Granger causal relationship. Now, that's a definition, and it allows us to understand what it is that people are trying to do. But it's not necessarily, one-to-one with how I think about causation, and I think how a lot of people think about causation. But at least there's a definition. But then we can start arguing about whether or not this is a definition that sort of. Does this make sense? Is this the type of causation or the type of inferences that we're interested in? And the answer may be yes or no, but that's something that we should debate. Dynamic causal modeling, on the other hand, so this has become very popular. It treats the brain as a deterministic, nonlinear dynamic system that's subject to inputs and produces outputs. And so what do they mean by causation when using DCM? Well, if you look through the papers, this is the closest to a definition that I've been able to find. And it says that causality in DCM is, using quotes here, it's used in a control theory sense and means that under the model, activity in one brain area causes dynamics in another, and these dynamics cause the observations. Now, if you try to parse that, especially the second part, they're actually using the word cause twice in their definition of causation. So that, to me, is a little problematic because it becomes a little circular there. But so in order to sort of completely understand what's meant here, I went in and started looking at the control theory literature. And if you look at the control theory literature, the definition of causation is that y depends on past and current values of z, but not on the future values of z. So in that case, it becomes very close to Granger causality, but I don't really think that this is what they mean. So I've been sort of trying to look around and try to find other definitions that might be closer to what they mean. And the best I found is this complex systems theory, where they say that Z causes Y if and only if Z engages in an activity to produce Y in mechanism. So that sort of sounds like what they're describing on the previous page, and this is sometimes referred to as mechanistic causation. So I think maybe the point I'm trying to make is clear here, is that here we have methods, we're trying to assess causation, and here we have methods for assessing causation, but we're not really been so stringent about what it is we mean by causation, and or whether or not this is a definition of causation that's sort of meaningful to us. And that's problematic, because the holy grail here is to find causal relationships among brain regions, but we haven't really even decided what that means. So that doesn't give me very much hope that we're going to be able to achieve that goal. So what I sort of suggest here is that when you're studying causation and trying to make causal claims, it's really important for researchers to A, consider what's meant by causation, B, define which causal effects you're interested in sort of estimating, and C, determine under which circumstances these effects can be estimated from the data. And I think that sort of short of making a sort of a framework like this, where you're trying to make sort of coherent, sort of causal inferences of this type, it's going to be very hard to sort of move the field forward, because we have to really know what we mean by, when we say that there's a causal relationship here, we really need to be able to pinpoint what it is we exactly mean about that. And so that's sort of a point that I want to sort of make in this session. So what's meant by causation? Well, there's not one answer to that. There's lots of different sort of concepts of causality. So now I want to go back to sort of first principles and talk about how different people think about causation. And so one of the sort of the original definitions is from David Hume from the 1800s. And he defined causality as follows. So there's temporal priority, so that's sort of like Granger causality, right? Z before Y. Spatial temporal contiguity, which is Z is near Y, and constant conjunction, FZ always Y. Okay, so in this case you would say, like, well, fire causes heat, right? So you light the fire before the heat comes, the heat and the fire are close to each other, and every time I light the fire, the room becomes hotter. So in that case, I might say that lighting this fire causes the heat. So that would sort of be the argument. And so this is sort of sometimes called a deterministic way of doing causation. You can very easily construct counterexamples where this falls apart. So for example, smoking. So we believe that smoking causes cancer, right? But it doesn't mean that every person who ever smokes gets cancer. So it's sort of the constant conjunction part of this sort of falls apart. F smoking, always cancer. That doesn't hold, right? Because you always get these people like, well, he was 120 and he smoked 5 packs a day and yada, yada, yada. So it's not always going to be the case. So under this sort of deterministic type of causation, smoking would not cause cancer. Okay? So now, how do we get around that? Well, then people started, fiddling around with different notions of causation, and then we have what we call probabilistic causation. That's that, Z before Y, so we have this sort of temporal priority, but then simply that the probability of Y increases if Z happens, right? So in this case, the probability that I get cancer, given that I smoked, is bigger than the probability of just getting cancer. So basically, I smoked before getting cancer, and the fact that I smoked increases my probability of getting cancer. Well, then I have this sort of probabilistic causation. Okay, again, we can make counterexamples. Here's one, where you have a barometer and you have a storm. So the barometer changes before the storm, it always does. And if the barometer changes to a certain direction, then the probability of getting a storm is higher. if we know that information. So in that case, in a probabilistic causation term, the barometer changing would sort of cause the storm, which isn't really true, right? Probably not. So this has led people to a different notion of causation, and this is what's become very, very popular in both the computer science literature as well as the statistics literature. And so this is sort of the notion of causation that statisticians and computer scientists use, and that's sort of a counterfactual type of causation. And that says that if Z had not occurred, Y would not have occurred. Okay. So let's unpack what that means, and let's unpack it with this little example here. So this fellow Bob, he's sick. He takes medicine and gets better. So he took the medicine, he got better. Did the medicine cause Bob to get better? Well, in a counterfactual sense, we don't know that because we don't know what would have happened had Bob not taken the medicine, right? So basically, if Bob didn't take the medicine, one of two things could have happened. One is he would not have gotten better, so he would have remained sick. Or the second would have been he would have gotten better regardless. So according to A, taking the medicine caused Bob to get better because had he not taken the medicine, he wouldn't have gotten better, right? So everything else was equal. He took the medicine, he got better, and had he not done that, he would have not gotten better. But under B, he would have gotten better regardless. So it doesn't matter if he took the medicine or a sugar pill or a placebo or whatnot. So it wasn't the medicine that caused Bob to get better. Maybe it was just time. Okay? And so that's sort of the idea behind the counterfactual statement is that you have to basically think about what happens in two different settings. One where you do the experimental manipulation and one where you don't. So here the experimental manipulation is taking the medicine, and you want to compare that with what would happen if you did not take the medicine. So how do we work with these things, these counterfactual ideas? Well, there's lots of different ways of doing that. So computer scientists have ways of doing this, and statisticians have a way of doing this. And I'm going to talk about how statisticians usually talk about it, and this is usually used in something called the potential outcomes notation. So counterfactual ideas, as I've talked about now, can be expressed using potential outcomes notation. And so basically, here we can suppose that each individual in our population can be exposed to two different treatments. So it's either a 0 or a 1. If you're in the 0, then you get a sugar pill. If you're a 1, you get the medicine. Okay? So those are the two possible treatments you can get. Bob could have either gotten the medicine or he could not have gotten the medicine. So in this case, each individual has a potential outcome under the treatment denoted Y0 and Y1. So these are two possible outcomes that could have happened, right? Had I given him the medicine, I get to observe Y1. That's his score under the treatment. And Y0 is what would have happened had I not given him the medicine. Now, if I want to look at the causal effect of the medicine, what I really want to look at is the difference between the two. Because Y1 is what happens in the world where he got the medicine, and Y0 is what happens in exactly the same world, but where he didn't get the medicine. The only thing that differs between these two different worlds is that he got medicine in one and didn't in the other. Okay? So the problem with that is, so that makes sense, to me it makes sense to think about that in a causal sense, because here we have sort of two parallel universes, one in which Bob took the medicine, one in which he didn't, and we're just looking at the difference in how his reaction to the treatment is. And so that's a clear sort of causal term that we can sort of discuss. But the problem is that we have sort of a missing data problem here, because I either gave him the medicine or I didn't. If I give him the medicine, I observe Y1. If I didn't, I observe Y0. So only one of these potential outcomes is observed. So this is sometimes called the fundamental problem of causal inference, is to make a stringent causal statement, I often need to understand what would happen if I had made a different treatment decisions or made different decisions throughout here. And here, so basically what this becomes is it becomes sort of a missing data problem. And I'm going to try to illustrate this as we move forward. So what happens is, because we only see a partial amount of data, we try to focus on introducing sort of defendable assumptions that allow for the estimation of average population effects. So often what we do when we can't measure everything that we need to is, as quantitative folks, we usually make assumptions to cover for that. Right? And so we've talked about assumptions during the morning and how some are good and some methods allow for different assumptions, but that's usually when we don't know something, we make assumptions and we try to use that to improve our models. So this kind of illustrates the differences between the different modes of causation. So these earlier models define causation in terms of observable phenomena. So in the Hume model, it's did the medicine cause Bob to get better? Well, he took the medicine before he got better, and it was in close proximity that he took medicine, and every time Bob takes the medicine, he gets better. In that case, according to Hume's deterministic model, the medicine causes him to get better. So if you think about that, basically what you see is sort of the definition of causation and the mode of inference is the same in both cases there. And that's not true in the counterfactual world, because in the counterfactual world, you define causation in terms of a comparison between an observable and an unobservable event. So I gave you the medicine, so I observe what happens to you when you got the medicine, but I never observe what happens to you when you didn't get the medicine. So one of them is observable and the other is unobservable. So that's a problem. So how can I get around that? Well, I have to make these assumptions. And so, but the key thing here is that the definition of causation, what I mean by causation, is sort of fundamentally separate from the manner in which it's inferred, how it's estimated. And that's a key sort of thing in understanding how causal things work, is that first you have to sit down and estimate, in a perfect world, what do I mean by causation? And then thereafter, you have to sort of figure out, how can I use these available methods to estimate that? And I think that's an important point, and I'm going to try to illustrate that with this little example here. And so we have 6 subjects here, so I get 6 of you, and I put 3 of you in the treatment group and 3 of you in a placebo group. And suppose we measure an outcome for each subject. So this treatment is supposed to lower your blood pressure or something like that. And so we want to determine what effect the treatment has on the outcome. So we think that people in the treatment group are going to have lower blood pressure than people in the placebo group. We hope so, at least. So in this case, let's define some notation here. So here, z is equal to 1 if you're in the treatment group, and z is equal to 0 if you got a placebo. And let's let y be the outcome. That's how much your blood pressure lowered. So in this case, now there's 2 possible outcomes that we could have observed if we're using this counterfactual language. In one world, Tor could have been placed in the control group. In this case, I would observe y0. That's how much his blood pressure lowered had I given him a sugar pill. In an other alternative world, I would have placed Tor in the treatment group. In that case, I would have observed y1, which is his outcome had he been treated. Okay? So at the start of the experiment, these are 2 possible scenarios. One is I give the medicine to Tor and I observe y1. The other is that I put Tor in the placebo group, or I randomize him to the placebo group. In that case, I observe y0. So I'm only going to observe one of these 2 guys, because I can only experiment on Tor once. He doesn't allow me to do too much to him. But if I want to know what is the effect of this medicine on Tor's blood pressure, what I really want is I want to know the difference between y1 and y0. So when I gave him the medicine, did his blood pressure change more than when I gave him the placebo? That's what I want to know. That's a causal effect that I think that at least I can understand. That's like there's 2 possible situations. You get the medicine or you don't. Here's what happened when you get the medicine. Here's what happens when you don't. And this is the difference. That's sort of a pure causal effect in the sense that everything in these 2 worlds are the same, except that in one world you get the medicine and the other you don't. Right? So in this case, this is sort of what we want. What I believe, this is a definition of causation that I can understand, and that I believe would be something that would be quite useful. But the problem is, again, is that only one of the potential outcomes can be observed. Okay? So this is what I mean by causation, but I can't estimate it, which is really frustrating. So maybe instead of looking at just TOR, I'll look at the population. So here I'm looking at the average difference between these two guys. And let's look at the table here. So here's a table. So 3 of the people were in the control group. So for them, you observed these Y zeros. And 3 of the people were in the treatment group. And for them, you observed the Y ones. But we never observed both for both those people. So we have a missing data problem, right? So the fact of the matter is I can never estimate this delta, which is the average difference between these, because I don't have the difference for anyone. But what can I do? Well, I can estimate D, which is basically just the average treatment response for people in the control group versus the average treatment response for people in the treatment group. That I can estimate from the available data, because I have 3 people in the treatment group. Their average is 0.6 or something, I don't know if that's true, or 0.5, that I know is true. And people in the treatment group have another average, and I can look at the difference between them and see what, so that's something I can estimate from this observable data. But this is not what I want to estimate. Delta is what I want to estimate, D is what I can estimate. So D is showing that there's an association between the treatment and the outcome, but delta, if I could show that, would show that there was a causal effect. So that's, I think this is an important point, because most of our methods are estimating the Ds of the world. So they're estimating that there's an association between these two things, but not getting at the causal thing, because they haven't defined what the causal thing is that they're interested in. So what do? Well, we want to figure out how to get around this, and so we want to find a way. So is there a way that we can equate D and delta? And so the way that we can equate D and delta is by making assumptions. And so basically, a non-zero value of D implies that the variables are associated or correlated, but not that Z causes Y. So how can we equate these two guys? Well, basically, we have to assume that the potential outcomes are independent of the treatment assignment. That's an assumption that you have to make, because that allows you to get rid of these sort of pesky conditionals on D, and that gives you a delta. So when is that true? Well, that's true when you randomize people into treatment and control groups. And that's why most of these sort of FDA trials that people do use randomization, right? Because randomization is great, because it controls for a lot of problems in the world. And so if it is true that these guys were randomly assigned to the different groups, what happens is that you can sort of fill in the blanks with the other people, because the people are sort of exchangeable with each other. So basically, I observe Y1 for these 3 people, but that's sort of what would have happened if I had observed Y1 for the other 3 that I didn't observe. So that's what randomization sort of gives us in that case. Does that make sense? Okay. So basically, this holds if the treatment is randomly assigned. So under randomization, we can make causal inference in this simple problem. So remember I went back and said this is the framework that you need in order to understand causation. Well, the first thing I said, well, you have to consider what's meant by causation. So what I said is my definition of causation is this counterfactual thing where you have kind of 2 parallel universes, one where you have the treatment, one where you don't, and you look at the difference. That's my sort of what type of causation that I use. So check on that. The second thing is I want to define the causal effects of interest. That was my delta, right? That was the difference between Y1 and Y0. So that I did. So that's what I want to estimate. However, I can't estimate that from the data. So now I need to understand under which circumstances can I estimate the effects in 2 from the data. And now I can estimate this delta using my D in the previous slide when I assume that the guys were randomly assigned to the treatment groups. So check on that. Okay? So this is just a little cartoon thing, but showing what has to go through your mind when you're trying to make sort of causal conclusions. You have to basically be able to convey what you mean by causation and what it is that you want to define, and then figure out how the heck can you do that from your data using whatever method that you're interested in. All right, and so we've used this in a bunch of different things, and we're big fans of this, and so we've used this to show that, that you have to sort of adjust for systematic errors in bold fMRI. We talked about Granger causality and SEMs and things like that, but I'm not going to focus on that because I want to get to, with the remaining time, to kind of tie this into a brain. So you're saying, so what about this? How does it impact my life? Well, let's consider a brain example here. This is a three-variable structural equation model, sometimes called a mediation model as well, if you're a psychologist. They love that stuff. So here we have three variables. You have a treatment, you have an outcome, and you have a brain response. And let's assume that each subject receives one treatment each, just to keep it simple. And so let's say that, even if you randomize the treatment that the people, let's say that we're interested in what assumptions are needed to make a causal interpretation of this link from the brain to the outcome. Okay? So this is something that we're interested in. Like, is the brain causally related to the outcome? Well, let's just make it simple. Let's say that people are either high responders or low responders in brain activation. And let's say, basically what we want to do is we want to look at, well, what's the difference between high responders and low responders in terms of outcome? That's what we want to estimate. That's the causal sort of thing that we want to do. If I could switch you from being a high responder to a low responder, how would that affect your performance on this test? That's basically sort of the causal effect of interest that I would be interested in trying to obtain here. Now, when can I make that thing? Well, there's a lot of assumptions that need to be true, but one of the key ones is that there can be no unmeasured confounding for the MY relationship. So basically, there can't be any latent variables that affect both M and Y. Okay? And this is generally not possible to test in practice, but it has to be assumed in order for us to be able to make sort of causal conclusions. So when would this be false? Well, I can just, in a sort of a cartoon way, say that, well, let's say that there's genetic reasons. There's genetic reasons why you respond higher, your bold response is higher, and there's genetic reasons why you perform better on this test. Okay, that's a confounder, and that's going to screw up that relationship between the brain and the outcome. Here's another one. Let's say that the outcome is something related to, say, ADHD, whether you have ADHD or not. And let's say the kids that move a lot have ADHD, but kids that move a lot also, well, not necessarily have, are more likely maybe, or kids that move a lot maybe have higher estimated brain response because of their motion. In that case, it screws up the link. So here you have these sort of measured or unmeasured confounders, which are not taken into consideration into the model, which is sort of ruining our causal inferences here. So this is just a cartoon example, but I decided that, well, we have this human connectome project data, so maybe we can make this more tangible. So let's look at sort of a mediation which people have been sort of interested in, and this is the link between intellect and accuracy on working memory, sort of an NBAC task. So here, what we're interested in is this activation in a particular brain region. So the posterior medial frontal cortex mediate this relationship between intellect and accuracy. So if I took 100 subjects and estimated this, and I found, indeed, there is a significant link between PMFC and accuracy on an NBAC task. And that corresponds to things that have been found in the literature. And so that's really exciting. And I want to make a sort of a causal claim about that, and I want to crow about that and whatnot. However, another thing that the Human Brain Mapping Project has done very well is given you a lot of sort of demographic thing. So it doesn't take very long to look through the demographics and say, well, let's look at SES, so socioeconomic status. So it turns out that SES, people with higher SES, have higher brain response in this, and they also do better on the NBAC task. So if you do that, now this has gone down. It's not significant anymore. That's not really the point whether or not it's significant, yay or nay. That's just sort of a binary decision. But what you're seeing is that previously we had a biased estimate. So we were overestimating the link between them, and that was we were a little bit too optimistic. So by taking into consideration these confounders, there still might be a link between them, but we've gotten rid of certain biases that have been screwing up our sort of causal relationships and whatnot. So it could be that this link completely disappears, or it could be there, but it's definitely much weaker than had you not taken into consideration all these covariates, or this one covariate. So basically, the argument here is without sort of direct manipulation of neuronal activation, it's really hard to make causal conclusions about brain activation. And so in particular, lots of different confounders can give rise to biased results. And this is something that I don't think that we do enough. We write our little graphs, but we don't take into consideration all the possible confounders that are present. And this is no doubt sort of biasing results and giving sort of erroneous findings. So how can you get around this? Well, I'm going to go quickly because I don't have that much time, but one way to get around it is better experimental design. If causal inference is interesting to you, you should figure out what it is that you want to causally find and incorporate that into your experimental design. And so the benefit of working in one of these causal frameworks is it really imposes a degree of rigor to the design process. Another thing that you can do is something called matching. So in this case, I said that there might be sort of genetic things that are causing you to be high responders in brain activation and doing well on NBAC tasks. Well, in this case, maybe we should match on that and just compare people that both have the same genetic information or the same covariance. So that's another trick that people can often do, is to sort of try to find a twin or something like that, or a group of people that are very much like you in all covariates, and try to look at the differences. One was treated and one was not, and try to use that to look at potential differences in the outcome. And so propensity scores are one way of doing this. Finally, another way of doing all this is what Gary talked about. Gary was talking about neurostimulation. I think that's incredibly exciting, because if you have these sort of networks, you could basically, in an ideal world, sort of randomize brain activation in the sense that I can maybe make you a high responder or a low responder in this task by zapping you while we're doing it. So playing around with that, I think, is hugely promising for sort of causal inferences and the like. Finally, I think that sometimes, with the final 2 minutes here, I just want to say that I think sometimes we're a little blasé about doing our causal inferences. So ultimately, sort of guaranteeing the validity of any causal inferences is difficult. So I really think that we have to, anytime we want to make causal inferences, we have to work really hard to disprove it. Okay? So basically, the idea here is that I think that researchers should try to seek to defend hypothesized causal relationships by seeking data that subjects their theory to sort of repeated falsification. Try harder and harder to sort of break your method, right? And that goes back to Karl Popper, and he was stating that confidence in a hypothesis doesn't depend on the number of tests it withstands, but basically the severity or the range of the test to which it's been subjected. If I do the same test on the same population over and over again, the biases are going to carry forward. But if I do the test and change it and create a wide spectrum of different ways of testing that and make it more severe, then I'm going to believe the results more. So repeatedly testing a hypothesis with certain biases will just replicate the biases if you keep doing the same thing. So basically, the take-home point here is when randomization is infeasible, only creative and sort of severe falsification tests can really help transition from association or correlations to causations. And so this is something I've adopted from a joint paper with Tor and Wani Wu. This was about a biomarker development using machine learning, but it actually applies very well to causal inferences as well. So first you fit your DCM model or whatever you do to your population, but then you sort of start widening. If you find something where theoretically you believe that there's a causal relationship, you have to start expanding the problem and trying to get different populations of subjects, different scanners, different this and this, and try to make it as broad as possible, the differences between the data. And if your results hold up again and again and again, then we can start believing what it is. And I think that just a single paper on a single 20 subjects, that's not really going to make me believe it. I think it has to go through a very rigorous sort of a process of falsification and overcome that in order for me to truly believe that it's causal. So that's just sort of just a thought point for the future. So in the conclusion, in the last couple of decades, researchers have sort of generated a literature on causal inferences, and it's based on this sort of idea of counterfactual conditional statements. It allows for a definition of causal estimates independent of the method used for estimation, and it allows one to give assumptions or conditions under which sort of commonly employed estimators can be given causal interpretations. So if I believe in my definition of causation, I can tell you under which assumptions DCM or SEM or Granger causality estimates those things, and they tend to be quite strict. So finally, I just want to thank Michael Sobel, my former colleague at Columbia, who taught me all about causal inference. I want to thank Tor, because he's being a good colleague, and he invited me. Thank Funding, and I thank you for your attention. And then I always end with some shameless self-promotion that Tor and I have a Coursera class online, which you can go and watch if you're interested. Okay, thank you.